So here we are looking at sample formula sheet, the common equations in mechanics of materials. So we are starting straightforward. We're going to deal with the ones that are very common. Okay. So then we see this one for instance, and then this is the uh, moment of inertia for torsional moment, right? And then what is inside here is basically telling us that the section that we're talking about is not a solid section, meaning what was the name? Meaning that it's not a solid section, meaning the inside is empty, right? So like if you have something of this sort, it has a particular thickness but the inside is empty, right? So that's what it says about this formula. The next one that we have here is the second moment of inertia for bending, right? Which is this one right here, right? And we see this, and then the black circle inside this just is telling us that the sample that the moment of this, we use this formula when the sample is a rod, right? A rod, a shaft, or cylindrical shaft, or something like that. But then the stick, right? It's a solid one, meaning the inside is filled. There's no hole. There's no hollow. That's what it means, right? And then we have this. So, okay. And then we have this right here. This is also the second moment of inertia, but this time around, it's saying that the rod shaft of the cylindrical what's the name? Cylindrical sample is hollow. That's what we see. So that's when you use this particular formula, right? Then again, this is deflection maximum. If you don't see V and see V, if you don't see Y and see V max, they are the same. Basically deflection. And then this is used for what's the name? This is used for columns, right? And then not just any columns, but columns that are eccentrically loaded, right? Meaning that the loading is not at the central axis of the column, right? That's when we use this. This E here is not Euler's number. Again, there's no Euler's number. It's something we call eccentricity. So the E that we are seeing there is not Euler's number, but something that we call eccentricity, which is basically the distance between the load line, the line of action of the load, and then the central axis, right? This is just pi. This is just this. And then one thing we should note here again is that this sec here is for all of this, right? So basically we have a bracket here, right? So sec of all of this times this minus 1, right? That should be very clear. And then one thing again, now if you are doing computations involving this sec here, what we are doing here is not concerning angle. You should make sure that you do everything in rad, right? Everything should be in rad because of this sec here. Then if you are using a calculator that doesn't have sec, remember that sec is basically the reciprocal of course. So, right, so if you're pointing something of that sort, you get to know that this sec, right, of pi on 2, which we said is this way, times the square root of p on PCR, and this PCR here is the same as 1 on cos the same thing, which we have pi on 2 times square root of p on PCR, right? So these and these are the same, just that the sec is the reciprocal of, sorry, cos, sec is basic reciprocal of cos, yes, reciprocal of cos, right? So that's what we have here. This doesn't look like 11. This one, but just saying that these two are the same. These two are the same. Okay. And then this R that we are seeing here is basically basically the formula for finding the neutral. This is the general formula for finding the neutral axis. But then this summation here is just trying to tell us that for composite figures, basically the Rn, let me just write it. It's either you see just the capital R or you see Rn, right? But basically the formula, this is a general formula for it. But since the summation we are seeing here just trying to tell us that we are finding the Rn or the neutral axis, right, for a composite figure, right? Basically if let's say you have a figure of this sort, something like this, if you decide to section it into three parts, if you find the area of this, area of this, area of this, you add them all. That's what we're seeing. And then we have a summation of the integration of this, right, which is basically over the entire area, right? And then we have a one on this. What this means here, respect to DE, is the same thing, right? But just that they've made it summations, but all over on E, and then we have E like this, and then we have R, right? The same thing, but just that we are integrating this, right? And the DE is here is the same thing. But this run right here is for finding the neutral axis for composite figures. Are you okay? Composite figures. Composite figures. What do we have next? Let's see. Okay. One common thing that we are seeing here too is this. This is basically a discontinuity method that we use Macaulay functions to describe the concentrated load, concentrated moment, point load, or yeah, that's what we are using to describe them. And this we've seen so far that there's a part of it. So basically for that one, we have the basic form is this way. It's either a plus or minus depending on direction, and then you have the Macaulay bracket, right? And then we have an x and minus and the starting position of the load, right? Which is we use it to represent. In our discussion so far that the n here, the value for the n here depends on the load, right? So we either have a moment, a point load, a uniform distributed load, a linear distributed load. Each of them have their own value for the n, right? Okay. So for this here, we have the value of them to -2, -1, 0, and then 1, right? And then because we are doing the singularity method, we do a lot of integrations, which is what we have here, right? So what this here is saying is that if let's say you start doing the representation, so let's say you have something like this, x minus let's say a, we are choosing just a, right? And the n is you start, right? The lowest n that we can have is what, -2, right? So let's start with the lowest one. So when you're doing integration, what happens is that since it is negative, right, when you do the integration, you just add a 1 to this, so it becomes x becomes Macaulay bracket x minus a bracket, just add 1, becomes just -1. You don't do anything else, right? So where's that? Let's see. Yeah, so this is what they are saying here. So far as the n is less than 0, you just add 1 and you don't do anything. It becomes just the same thing. So that's what we've done here. It's still so if I'm integrating this again, so after I integrate this, it becomes this, right? So when I try to integrate this is what I get. So let's see. X minus a is -1, right? If I add 1, it just makes it 0, right? So when it becomes 0 like this, there's nothing I can do about it. I still leave it, right? But then if I before I do the what's it name? After that I do the yes, before I do the integration, I check, right? So before you do the integration, it's just 1. When I integrate, I get 0. I don't do anything to it. But if I do this, if I integrate this particular one, what I get is Macaulay bracket x minus a. I get to what, 1. When I get this one like this, the natural sense is to just bring that one I have here, right? Basically, there's one attached here, but without right, it's still the same thing, right? So just 1, and I bring that number that I had just there, I bring it down, right? This is what we get. Okay. When the x becomes, what's the name, either equal to 0 or greater than 0, so this is the formula part. So that's why we did the same thing here, right? So when the 0 was just as 0, it's just as 0, I add 1, I get 1, it's just 1, 0 plus 1, right? 0 plus 1, just 1. That's so it's still the same thing. But under is 1. If I try integrating what I have now, this is what it becomes Macaulay bracket. So if I try integrating this one, this is what I get. Yeah, x minus a, right? This one here, if I add and becomes 2, so it becomes this 1 on 2, right? This is what I get. If I try integrating this, I get this x minus a. This one, if I add, that becomes 3, and then 1 on 2 is already there. But then because I've integrated this new theory here comes down, becomes something of the sort. And then it's very safe if you do it this way, instead of converting it straightforward to, let's say, 1 on 6, right? Unless you're trying to get a final answer. Because when you do it this way and then there's a slight mistake along the way, you can get to know what's actually happening, that, oh, what did the mistake happen or something, right? So it's safer to do it this way than to simplify everything, especially when you are going with the process. That's what this one is saying here. Okay. Then again, this one here is still the Rn, the general formula, but as we were saying, this one here is for a composite figure, right? This one here is just for a simple figure. Okay. And this E that we have here is the eccentricity that we said earlier. Eccentricity. This eccentricity is basically the distance between. So if you have a figure of, let's say you have a column, right? This sort. This is the centroidal axis. This is the centroidal axis. This is the centroidal axis. I'm going to do it very fast. Let's say the loading is about here, somewhere here. The eccentricity is basically the distance between these two. So this is the distance between these two, right? That's the eccentricity. The general formula for this. That's the general formula. This R here, and this one right here, this one here right here is same as the Rn here, right? But this one is a specific one for the trapezoidal section, something of this sort. Let's see, something of this sort, right? But then the slight difference here is that let's see, the basic formula for the Rn, the Rn of a trapezoidal section is this. We have a A, and then we have a B, and then we have a, then we have RO, RI, right? This RO here is just the outer, this inner, the same outer inner here, right? But then the difference here is that this A here is the same as the base times the height, right? Base times length, RO, RI is the same as R2, R1. So this cancels this out. That's why we have this one right here. So it's the same thing, RN for a trapezoidal section. Okay. Then this one here is basically for, what's the name? Castigliano method, right? Or the energy method, or the strain energy method, right? This right here is the deflection. It's basically similar to the equation for the slope, right? But the difference is that for the slope, if you don't see this and you see this, it's the same, right? For the slope from action and entire beam, this one here, we do the difference partial derivative with respect to, for the slope, right? We do with respect to p, right? And then we have this m e I dx here. One thing to help, yeah, partial derivative with respect to p. But then for the slope, which is this, right? If you see this, right? The integration acting on the entire beam, the entire length of the beam, this, but here we do the partial derivative with respect to m. So we put something, where is it? Yeah, put something here like this. But the rest is the same. ei dx, right? Yeah. So what's next? This one right here is a trapezoidal section, and this we usually see it in curved beams, right? And then this is the Rn for it, right here. This is the Rn. This is basically saying that there's also an Rn formula for this, right? But this things if you want to do it in a composite way, right? All depends on you, but the moment you understand, you can use whichever one that you're comfortable with. This is the area for it, right? It's trapezoidal cross section. And then this one right here is the maximum stress in a column that is eccentrically loaded. This here is the maximum stress in a column that is eccentrically loaded, as we're saying. So the load, the cross-sectional area. This E again is not the Euler's number by the eccentricity. This C here, so if you have a column, right? There's the, let's use this one. So a column, this is the central axis, right? This is the central axis, right? The C here is basically the distance from the central axis to the outermost fiber, right? So this right here is C, right? The R is the radius of gyration, which we see is the square root of I on E. This is the second moment of inertia. This is the cross-sectional area, right? Again, this sec here, as we said, is the reciprocal of cos. It's the same as cos reciprocal. Yes. And then, as we saw this one earlier, this whole thing is in one bracket. Then again, it's not always that you are given PCR. The formula might change slightly. So what happens is that you're not given PCR. You find PCR depending on the end condition. PCR, we have pi squared EI flexural rigidity. So if you don't see E and I individually, and here something like flexural rigidity minutes. At times E is given individually, you have to find I alone, but at times they are given together and as EI, which we see flexural rigidity, right? So if you see this, it's the same as EI, right? So if you, so that's it, right? And then we have on key L. This K here is basically the effective length squared, right? So if you are given one end fixed, so let's see. Let's take the common four end conditions, right? To see what happens for the PCR, right? So one is if you have a fixed and free, right? The other is if you have both hinged. If you don't hear hinged and you hear pinned, they are the same. This is both pinned or pinned. And then we have one hinged or pinned and then we have a fixed, right? And then we have both fixed. So let's see, both ends fixed, right? Each and every one of these have their own effective length. For this one right here, the effective length is 2L. For this right here, the effective length is just L. Let me send the color. For this here, the effective length is 2L. For this one, the effective length is just L. This one right here, the effective length is approximately 0.7 L. And this one here, the effective length is about 0.5 L, right? So depending on each one of this two here is the key, right? So this two here, the key. This here is basically one here we don't write is the key. This 0.7 here is the key. This 0.5 here is the key. So depending on that, you square with the actual length of the beam, you're able to find the PCR and then put it in, and you're good to go. Right. The next one we are seeing right below is the what's the name? The stress for what's the name? For a curved beam. So this one right here, as we are saying, is for a centrically loaded column, right? But for this one here, this one is for a curved beam. This is the moment, right? This is the what's the name? This basically has a common form. We have it to be this way. So basically, we have minus, we have m, and we have the distance between Rn and R, right? And then we have R again, and we have a cross-sectional area, and we have the distance between RC and the Rm. So if you see this, know that it's something related. If you see this one right here, it's something related to this, right? So this one right here. Right? So this one here is basically for, what is it? Yeah, this one right here is basically for curved beams, right? The same thing here. But there are times, this just by the way, for curved beams, there are times where the portion that you are trying to find the stress there is experiencing a direct force, so a direct stress, and and then again another stress due to the bending, right? So if you either have this, if it's having an additional direct stress at that point, you have this P on E plus the minus is still maintained, M Rn minus R, right? Hold on, Ra, right? Rc minus Rn. Right? So if it's having if the point or the system they are trying to find the, what do you call it, the stress at that point is having a direct stress there is this plus this, right? Plus this one. Okay. Move on. Then again, this one right here is still talking. This one here is still talking about the stress, right? Sorry, the deflection in Castigliano method. This one here is the slope in Castigliano method or energy method, as we're saying. So basically, for the one for the deflection, the only thing that changed here is this one changed to P, which we've seen here already. Where is it? So to P. The derivative is done with respect to P. So it looks like we've looked at all the essential things that we need to look at when it comes to mechanics of materials. The formulas that we usually use, right? Yeah. So yeah, so this is it. All right.